To kick off the second afternoon session is Ron Crouch. Ron hails from Joel, USA, and he's going to be educating us on fun ways to use qNMR to evaluate NMR experiment design. So that sounds great, and I'll just pass the mic to you, Ron.
Well, all right. I really wish to thank everyone for taking the time to attend this wonderful thing. And I must most humbly thank the organizers for giving me the opportunity to participate. So when I received this invitation from Darcy, he told me I could talk about absolutely anything I wished, so long as if it was about qNMR and had lots of deep sky images. So I quickly made up a title and wrote an abstract on a subject I really had no clue what the results might be. And somehow this seemed appropriate because the first time I met Bill, I had a conversation with him. And the gist of that conversation is that, you know, if you don't try something and have it succeed, or even better, mess up, you don't ever really learn anything. So this presentation is meant to be a whimsical blend of some universal truths about qNMR and some curiosity-driven observations. Well, there's some fundamental aspects of this, thinking that people may be here that are not really experienced in MR folks. So I'm going to introduce qNMR with the idea of running experiments, key parameters, and loosely defined different types, such as an internal reference, external reference. And we'll very, very firmly grasp the third rail of 2D qNMR. Now, when you talk about doing quantification by NMR, part of it is getting the data, but then the next part is getting the numbers. So there's different ways to do it. 1D peak height integration or craft, we'll touch on this. And in 2D amplitudes, we can look at traces. Delta is just a referral to one of the Joel software tools where I can extract cross peak volumes. And there's craft 2D. Now, the second part of this is we'll use some simple qNMR tools to compare the relative amounts of signal in different experiments. So we can think of it as the signal part in traditional signal to noise. So what is qNMR? I found this years ago at the Mystery Lab website. And so the core of qNMR is that ideally, it is the set of all peaks which can be assigned to a particular nucleus are proportional to the molar concentrations of the nucleus in that sample. But an important word is ideally. And one part of that is perfectly relaxed sample. So what does relaxed mean? So for the NMR beginner, you may have heard the word traditional wisdom that we really need to go at least 5T1. So what is that? So in this graphic, we're showing the relaxation at T2 in the transverse plane and in the spin lattice relaxation, and how the intensities follow an exponential. And so the intensity is 1, and it's minus the exponential of the repetition rate divided by T1. So if we just simply make this 5, then what we end up with, this value becomes 0.993. So that's where the 5T1 comes from. So for 7T1, it's even better. But measuring T1 is easy enough. We can do things like inversion recovery T1 and look at it this way, or we can look at it in a pseudo 2D processing, and basically not getting too tedious. At the null point, it's 0.69 T1. So we can get an idea on this and say, gosh, this relaxes fast. So we could go really fast and do good quantification on such a sample. But a thing that people don't often keep in mind is that if we have a pure compound, really, and we acquire an NMR spectrum and integrate it, the integrals will tell you about the relaxation. So in this example, this is estradiol, I do believe, and it's in a 400. What we see is an integral here that is obviously low, 0.81. This guy's also low. And so you go, well, what's going on? Well, we can look at this equation in reverse and compute that 0.81 intensity implies that our repetition rate was 1.66 T1 for this experiment without even measuring an inversion. So for reasonable results, if we wanted to quantify something using this particular molecule, the repetition rate should be increased at least by a factor of 4. Well, we do qNMR every day. We integrate spectra after all, but when we do the integration, it's usually as the idea of determining multiplicity, 1 to 2 to 2 to 3, or et cetera, that sort of a thing. But the idea of qNMR really is to change the integral units from something that is arbitrary to actual concentration. So wouldn't it be nice if we could just integrate this peak? And the answer is 22.75 millimolar. Well, and if you know it, we know purity. So there are several types, 3 key ones: external reference, internal reference, and standard addition. But today, we're really going to talk almost totally about external reference, qNMR. And so what is it? Well, it's a way to relate data from a real or synthetic sample of known to any number of similar compounds. So here's some slides from 2010 on this subject. All right, you have a bathroom scale. You would like to think that your NMR is at least as good. You just need to sort of tear the scale. So by example, I put in an NMR spectrometer, a sample of essentially 100% D2O. I acquire a deuterium NMR spectrum. And I set this saying, well, gee, it's roughly 100 molar, being 2 protons, but it really doesn't matter what do I assign this to. The fact of 100 would mean that that's 100%, pure and simple. So we've defined this concentration. So if we remove this sample, put in now tap water, and acquire a deuterium spectrum again. Now, this time we just changed the number of scans instead of 1 to 128 to be able to get a recordable spectrum, and we integrate it. And lo and behold, the answer is the natural abundance of deuterium. So external reference qNMR is a pretty nice, valid thing to do. Now, if we have 2 spectra, and by any software, any NMR vendor software would have the ability to show integrations in sort of an absolute intensity mode, unbiased by user assignment. And so in the Joel land, if you integrate a spectrum and do absolutely nothing to scale the integral, by default, it is this absolute intensity. So here's a sample of caffeine, unknown weight, unknown concentration. Here's a sample of phenephrine hydrochloride of known concentration. So I have an NMR spectrum, I integrate the methyls, I get a number. I integrate the methyl of caffeine, I get a number. A simple ratio of these 2 numbers, and I can compute the concentration of the caffeine. 25 millimolar. In actual fact, it's 23.4, which is pretty close considering this data was acquired a few weeks apart, actually. Now, if we do integration and make a decision to scale our data based on protons of 5 to 3 to 3 to 1 to whatever, one really nice thing in our world is if I look at the integral report for the sample, this absolute intensity integration is preserved. So it's impossible for a user to overwrite or misplace original information. So I can return to this sample 2 years later and relate it to something else directly. Now, there are many factors that can affect the strength of signals in internal reference. Well, obviously, the number of protons, the gain of the receiver, tip angle, recycle time, and intangibles, which are very important, such as the ionic strength, things like that. Well, the solutions to these are all really common sense. Understand your molecule. Very simple solution, use the same gain when you're comparing spectra, but gain scaling comparisons are very straightforward to do. It's just a log function. Use the same tip angle. You could also compute tip scaling. It's a sine function. Be very reasonable with recycle time. And if you're using external reference to another material, make sure you're comparing apples and apples. So don't be comparing a 400 millimolar salt solution with something in chloroform. It's not going to end well. Now, internal versus external reference. Let's just briefly touch on this. So here's a problem put back into the sky, and it's very much like external reference qNMR. So you have an observer here, an observer here, and their plan is they want to measure these two stars, and they want to report the exact magnitude and the colors of those two stars. But the difference is they're in different environments. Their viewing angle through the atmosphere is different for each, which has a profound effect on both color and magnitude. And there may be thin clouds at one site versus another. They may have different telescopes. So how do they get the answers? Well, they use external reference. So in this particular image, you may have three stars that are known and extremely well characterized. And if these are in the same field with this, we can use this digital image and look at the magnitude of any of these stars' intensities and accurately compute the color and the intensity. So that is, in fact, how external reference qNMR works. So we can get very nice precision, of course. It's not a big deal. You have, in this case, a maleic acid in an internal reference. We compare it with a simple molecule. I have no idea what it is. Looks like it's phenephrine. And we get the same concentration all within 0.4%. So we have pretty reasonable confidence that that's a good answer. Now, there are other ways to get answers. And certainly many of you have probably heard of Kraft. There's a very few publications with it. This is a recent review by Krish. That's a wonderful, wonderful article to read. So what is Kraft? Well, it separates each component into its parts. So when you look at an NMR spectrum, you have frequency, amplitude, phase, and line width. So Kraft works in the time domain to separate these components. And in the time domain, lots of awkwardness that's imposed before a transform is completely sidestepped. There is no baseline. Their phase does not matter. It's separated from amplitude. And overlap for establishing integration is completely unimportant, because so long as the sinusoids are resolved, we can determine the amplitudes. So this is a Kraft result, basically experimental spectrum, a Kraft spectrum, and the residual, which is just the subtraction, the Fourier transform subtraction of the FT of these two results. So we have visually, it gives us confidence in the answer, but really the answer are the numbers here. It's the magnitude. We can click on a number and look at the models and on and on. We can also define things like CSV files that are fingerprints. So we can define this particular molecule and use it as a fingerprint in a mixture and come back and have Kraft report the amount of material here separated by compound. This is a simple example with one material, but if I had fingerprinted 3 or 4 compounds, they would all be there. So Kraft also works in 2 dimensions here. So here's a HSQC. Here's a proton spectrum that is used as guidance to tell the Kraft what interferograms to look at when we do the 2D Kraft. So here's the 2D Kraft result. We have a table of amplitudes, but the real purpose of 2D Kraft is a little bit interesting here, in that even though this is only acquired with 64 T1 increments, okay, and no extension, that sort of a thing, Kraft takes every one of them and reconstructs it and extrapolates to as if it were 1,000 points. So the Y projection of this isn't in fact a depth 135, and even if you acquired very modest. So that is Kraft. Well, 2D qNMR, does it work? Of course it works. There's some wonderful papers and reviews. This is one I read years ago. Also, Patrick, who's going to speak at an upcoming IVAN seminar, is a leader in this area, and lots of wonderful, wonderful things to be found in these review articles. So As a way of a first example, I had to certainly pick santonin because if we look at the graphic for the Smart NMR conference, lo and behold, it has a proton spectrum of santonin. So here's an example of santonin. And what we've done is to verify that this works is we made up two samples, two different concentrations, and we've acquired a couple of HSQCs identically for each sample. So the pulse sequence is of no consequence whatsoever because we're using the same pulse sequence and the same acquisition parameters and resolutions in both. So it completely disappears from the picture. So these are the intensities, the volume extracted of all of the cross peaks of santonin for the two different compounds. We have a weak one and a strong one. Well, we can throw it all into a spreadsheet and we can get the numbers out and lo and behold, do a simple ratio. So we have, in this case, a known compound. The weaker one was 21.5 milligrams. Here's an unknown sample. We compare those in a simple ratio and we come up with 52.2 milligram is the amount of material that's in the tube. Well, I had no idea what was in the tube until I looked back in, of all things, a notebook and found that that sample had been prepared and it was labeled as being right at 51 milligrams. So it's a pretty viable result. So we can also use Craft 2D and extract. And here we're looking at a mixture of santonin again and adenosine. And so what we do is we acquire reference standard material for both the santonin and adenosine, and then we run a mixture and we simply compare the amplitudes for all of them, lots of spreadsheet numbers. But the bottom line is that using Craft 2D goes directly to a CSV file, which you see here. The santonin component actual concentration was 27.5. It's measured is 27.7, and the adenosine was 45.4, measured was 46. So I think I convinced myself that 2D qNMR does work. Now, there's a much more general approach to this that's worth mentioning. And this is a paper from quite some time ago from Markley's group. It's called HSQC0. And so it's an extremely clever idea. So we take what is normal HSQC here, but we sort of double it up and then triple it up. So we have HSQC 1, 2, 3, but if we take the cross peak volumes from these three peaks and plot them and look at the y-intercept, we've extrapolated to 0. And what is 0? 90 pulse acquire. So it's a very general thing. So Jose Napolitano Farina and Genentech looked at some mixtures here of ribofuranose and pyranose in the alpha and beta form with HSQC0, acquires some data, plots it, extracts it to 0, and lo and behold, we get answers out of that that are in very good agreement with many, many things. The Craft amplitudes, CT stands for cosmic truth. This is a quantum mechanical calculation. I encourage you to go here and look at this and actually use the tool yourself. It's fantastic. And traditional integration. So we get all very nice, agreeable answers. So armed with the assurance that qNMR, it actually does work, what we can do is look at some pulse sequences. So here is basic HSQC. It's a tango pulse in HSQC, phase detected, not in echo anti-echo. And here is what was published as the crisis HSQC. And the difference is these are paired adiabatic sweeps so that both the inept transfers and the refocusing for the multiplicity editing, these sweeps are timed so that the refocusing is going to occur at the likely true value of the carbon proton coupling constant. This is the crisis condition, and this was published long ago by Krish and these guys. So if we just look at these different cross peaks and compare it, these are the amplitudes we get. And so we saw, wow, relative to simple HSQC, it really is a significant advantage in sensitivity to do this. And of course, we can do it with gradient coherence selection as well, P and N, and we do lose intensity there, but it isn't a sensitivity enhanced gradient. So this does win. So we can predict our experiment behavior. So let's do all the hand waving right now and get it out of the way. So let's try to do something absolutely silly. So this is 1.5 milligrams in a 3 millimeter tube and a 5 millimeter probe in a 500 megahertz spectrometer. It's acquired 8 scans with 25% in US. So that's, maybe a 15-minute data set on 1.5 milligrams of salicylate. Now here is a sample of a 20 meg sample in a 5 millimeter tube in the same type of probe, but in a 400 megahertz spectrometer, 4 scans and linear. So this has signal and noise to absolutely burn. And so the real point is, can we approximate the number of milligrams in the 5 millimeter tube in this 400 from this 1.5 milligram sample in a 3 millimeter tube in a 500? Can we do this? So owing to frequency differences, based on strictly frequency, what we know is the 3/2 power of 500 versus 400. But in practice, some probe builder friends tell me that it actually is up the 7/4 power. So it's the 500 to the 1.75 versus 500 to the 1.5, but still you ratio those two. So I'll split the difference here, 1.44. So if we just simply take the ratios of the cross peak volumes we get in these two spectra, compute a value, scale it by the gamma, we come out with 18.2 milligrams, which is pretty darn close to 20 milligrams. So that's a completely silly thing to do, but it does in fact work. So let's look at a more germane sample. This is a HSQCO on 53 milligrams of santonin. Let's back up again. Now, here is an extremely low sensitivity experiment. This is in a 400. This is an overnight attempt to acquire a NJ1J dual optimized adequate on this sample, okay? Very low sensitivity experiment. So I get some cross peaks. The relative cross peak intensities that we're seeing here are 0.0001 relative to, say, call it 0.5. So we're looking at about a factor of 5,000 in cross peak intensity based on this single result. Now let's take a look at some fluorine NMR. Here's an interesting molecule. It's interesting because it's a horrible pollutant from Teflon manufacturer in the rivers. And this is called GenX. So it's a total peripheral compound. And we can look at the fluorine spectrum of it and the carbon spectrum, of course, with fluorine decoupling. And we say, gee, this is kind of nice. We can expand this fluorine spectrum and then we can look at it and say, oh, wow, we have a nice triplet here. It must be this guy right here. And then, well, what's with this guy here that's a singlet, more or less? It's really like a 1.8 Hertz J. This methylene circled in C is an AB quartet. So what we see, if we do some fluorine homonuclear decoupling, where we decouple this CFD, we get this result, and we decouple the CF3A, we get this result looking here. What we see is that, gee, that's got a geminal coupling of 150 Hertz, and there's a 4-bond J between this proton across oxygen to one of these fluorines that's nearly 20 Hertz. So this violates all the rules of proton NMR couplings to be expected. Now, looking at the same molecule, let's say, well, if we can decouple one, here we're looking at that methine, which is sort of a broad doublet of doublets, if we will. And there it is labeled D. If we decouple just the A, we see, in fact, that it is coupled to this. So that's a 6-bond J, and it's actually a significant coupling. But if we decouple both A and E simultaneously and acquire a spectrum, which is a fun thing to do and easy enough, we can extract all the coupling constants. And we see that, indeed, there's a 4-bond coupling going back 19.3, as we measured before, another 4-bond of 7 Hertz between the AB quartet in there, and there's 5-bond couplings to this methylene B right here from the CF. So the fluorine homonuclear couplings are a bit confusing, but HSQC can come to the rescue because we can spread all this information out into 2 dimensions. So of course we can run fluorine carbon HSQC. There's lots of nice papers about it. Bruce Adams did a paper long ago overviewing the sequences at that time. In my experience, a very simple HSQC that's routine and easy to do was published by Haitu and Krish, and it's a C2. So we use double BIP refocusing in the inept periods and then the BIPs here to get rid of the bandwidth issues related to fluorine. And we can in fact run a nice multiplicity edited HSQC. So if we take the HSQC for a perfluoro compound, now a perfluoroaromatic, we get nice 3 little peaks. And now we run fluorine carbon HMBC with a 20 Hertz J optimization. We can ratio the cross peak intensities. These are all roughly 0.9, and these are all roughly 0.2 in intensity. So we're looking at about a 4.5-fold signal intensity increase in the HSQC fluorine. Now, the other feature here is that if we look at the fluorine HMBC, it's a big problem, and that is every fluorine is coupled to every carbon, essentially. So from a structural information point of view, we have too much information. So we can do some expansions here and generate a really pretty plot. And I actually use JSON, which is a new NMR processing software I'll refer to at the end, to make this pretty graphic in just a couple of minutes. And another feature that comes up with fluorine is that the chemical shifts are isotope shifted. And this is in the HMBC. So we see the direct is not centered at all, and all of the one bond, all of the long range are slightly different positions. And we're just monitoring this individual fluorine here. So what are we going to do? Well, first, be sure of all the assignments. So we know everything. We have an inadequate. So we've assigned all protein, all the carbons. We know all of the carbon-carbon coupling constants. We also know all the fluorine-carbon couplings here. So now, before we go to something much more direct to that problem, let's take a brief look at fluorine nitrogen. And I was looking for an example, and I didn't really have what really would be appropriate for this molecule, and that is just a simple, plain old, dyed in the wool absolute value HMBC will be the way to go on an experiment like this. But I had a phase sensitive HSQMBC, fluorine nitrogen. And so what we see is that the fluorines 5 and 2 couple the nitriles. The interesting fact from the are twofold. One, these intensities are very, very low, 0.0004 relative to, remember, 0.9 was the intensity of the HSQC. But there's a 4-bond coupling. This fluorine couples that nitrile. This fluorine couples that nitrile, okay? Both fluorines couple the N7 up here, the aniline, which is folded in here as well. And it's a very, very small value. So again, we have a huge loss in signal, and it means we need to probe our experiment and maybe pick another choice for doing fluorine nitrogen. So again, here's the numbers. Fluorine carbon HSQC, the HMBC 0.2, and this is about a factor of 50 below the carbon HMBC. Now, recently we published a note where about the development of fluorine carbon adequate. So this is a 1,1 adequate on this molecule, which we see is completely unambiguous. F6 shows connectivities to 1 and 5. It's adjacent partners 5 to 4 and 6, of course, and F2 to 3 and 1. So there's no ambiguity whatsoever. So what kind of intensities are we recovering? Now, what I'm not going to get into, because it would be really fairly tedious, is there was a fair amount of pulse sequence development here and ended up on a double BIP for the first inept, a BIP for evolution, a BIP for the single quantum, double quantum, single quantum conversion, and in the PFG decode, but in the sensitivity enhancement portion of the HSQC adequate, the double BIP trick did not work. We could write experiments that would work perfectly well with proton carbon adequate, but they utterly failed with fluorine carbon adequate. And exactly why that is unknown and is an interesting fact. So for now, we're keeping this simple. So if we look at the intensities of that, we recover 0.003, and that was relative to 0.9 for the HSQC. Now, a nice technique to measuring J's from a really nice paper, Bermal and guys, back in 2003, is the idea of J modulation. So we can take any adequate experiment and we can drop this little module in there, okay, and turn it on and off with a flag. And what we end up doing is acquiring, in this case, a 1-1 adequate. But the difference is we've introduced sort of a pseudo second dimension to where this is a coupling constant that could perhaps be scaled up 20 or 30 times of the actual value. So I can measure those separations and get the 1 bond J out of it at the same time. So if we look at what's in the box, and the sum of that, 0.003, the sum of these two is 0.0019. If there were no losses in this experiment, they would be equal, right? But what we're recovering is it's about 63% of the signal. So this J modulation in front of this first carbon transfer, it does cost us a little bit of intensity, but at least in the case of 1-1, it's not severe. In long range adequate, it's a very severe penalty. Bottom line, if we look at NJ adequate, it's the same thing, very, very low intensities. We need to look at what we can do to pull these up, or maybe perhaps more accurately measure them. In the experiment, we're limited in time because we don't have this is decremented. So we have a limit of how long, with the fact that the J, carbon J, is large. So we do use linear prediction, but done through NUS extrapolation, and we can recover peaks that are unresolvable with the allowable resolution that you can actually acquire by normal technique. So thanks to the organizers, the telescope mount at Seton Hall, Gary and Jeff Rabb at Merck, Misha, also known McCall, Alexi, Thomas, UNCW, at Genentech, Jose and Dave Russell, Joel, a host of people, Joel UK, the family over there, and of course, Manuel Perez and the entire JSON team, and go to www.joeljason.com and look at something really interesting. So thank you very much for your time.